Hello everyone, today I'm delighted to present a live demo of MonacGraph, a monadic second-order logic-attended graph database with community-aware storage. The data management panel is on the left. Here we can use the Create Test Data button to generate a sample graph dataset. As you can see, we've generated a sample graph with 4 vertices and 3 edges. Beyond generating test data, MonacGraph also supports custom graph uploads. We can upload 3 optional files. First, the graph topology files set up the graph core structure. Then we add optional details, vertex properties for vertex attributes, and edge properties for edge relationships. Then, let's demonstrate how MonacGraph executes queries using Gremlin, our custom extension of standard Gremlin language that adds support for monadic second-order logic queries. Gremlin is fully compatible with its standard Gremlin syntax. As you can see, this example query simply retrieves information for all vertices. We can see the result displaying all vertices along with their attributes. Now let's focus on the core strengths of Gremlin. Its native support for monadic second-order logic query syntax. This second-order query checks if every person knows someone else. It works by checking that for every vertex in the graph, there exists at least one vertex y such that there is a direct outgoing edge from x to y. The result is false since Mona has no outgoing edges. This query efficiently finds all clicks of size greater than 1. It works by checking that for all x and for all y in the set, either x is same vertex as y, or there is a direct edge connecting them. Finally, we ensure that the result is a valid click by checking the set size to be greater than 1. We can see that there are 32 valid clicks matching our criteria. The subset visualization panels displaying the induced subgraph for each click. We can view vertex or edge IDs, labels, and properties, either by hovering our mouse over the corresponding vertex or edge, or by checking the vertex property panel on the right. This example shows how Gremlin queries for all weakly connected components. The results show our graph has only one weakly connected component. This example shows how Gremlin query for all strongly connected components. Furthermore, we can easily add constraints using Gremlin syntax, for instance, to find the SCC that contains Alice. MonacGraph employs an LSM community storage architecture with community-aware partitioning, allowing us to run community-based queries. This example shows how programming queries for all LSM communities. Since the graph is densely connected, it forms a single LSM community. To better illustrate that, let's add an isolated vertex named Miles. Now, when we rerun the query, it will return two distinct LSM communities. This example demonstrates a BFS query. It retrieves and displays information about all vertices reachable from a specified starting vertex. We can arbitrarily modify the starting vertex for the BFS traversal. Finally, we can clear the entire graph with Clear Graph button. That concludes our demonstration of MonacGraph system. Thank you for listening.